So this is the foundation paper, Year 11, Unit 6, for the double award, and 60 marks available. There's your front sheet with your formulas. So the first question is on thinking distance, break distance, and overall stopping distance. So the first question, you need to recognise some sort of trend by year, so 6, 9, 12, 15. So the answer is going to be 18 there. And then if you can also notice that thinking distance plus breaking distance gives you stopping distance. 6 plus 6 equals 12, 9 plus 14, so on, so on. So 18 plus 56 is going to give you a second mark there for 74. Describe how worn tyres affects the following. So thinking distance, there's no effect because it's not a factor, but it's going to increase your braking distance. These are all things that affect your braking distance, things like weather conditions as well. And then down here, you've got distractions using a mobile phone. So that's going to increase your thinking distance now, the time it takes you to hit the brake pad, the brake pedal, sorry. And then, but that's not going to have, once you've hit the brake, it's not going to have any effect on the braking distance. And that's that question. So on to space then. Solar system was formed by collapse of clouds of gas and dust for 2 marks. Okay? So that's whether it's a star, whether it's a solar system, whether it's a planet. It's all going to be the gas and dust collapsing under gravity there. You've got a table of data. So we're going to read this data. We're going to interpret this data. Now describe how the temperature of the planet depends on the distance from the sun. Well, let's have a look at the temperature and then the mean distance. So you can see that these are arranged as they get further away, and the temperature is going to drop. So it says temperature drops. Identify the planet does not follow the trend. It's going to be Venus, like it goes from 430 to 465 and then back down. It drops all the way then. Last bit of this question then. There's an asteroid found in the asteroid belt. Estimate its temperature and its orbit time. And the way I would do that, I would need to know that the asteroid belt is found between Mars and Jupiter. So when I'm looking at temperature and orbit time, I think the other one was, you're looking there. So anywhere between minus 20 and minus 150. So minus 21, minus 149 would be any answer there, and then 3 to 11 there. And that's what I've got there. Suggested that greater mass of a planet, there's going to be more moons. Generally, that's the case, but Mars has 2 moons, and Mars is smaller. It's got a smaller mass than Earth. So again, it's kind of like Venus with the temperature is higher. So it's a bit of an anomalous result there. It doesn't follow a trend, but it is what it is. And again, I would have got that from the data from the table. I would have listed the number of moons, and then you'd look at the mass of the planet. On to Hooke's law then. So you've got a little bit of information there telling you about the elastic limit, point E. So a lot in the question there, and then it says, use the graph to find the largest force the way Hooke's law is still obeyed, and that's going to be at point E, because it told you from the question. So the force is going to be 50. That's the largest force, and then it starts to tail off then. So 50. Explain whether this particular spring is suitable for the use on a trampoline. Well, has passed the elastic limit, so no longer obeys Hooke's law, so will remain permanently stretched. So it's not really suitable, is it? Okay, so 58, and we're looking for a force of 50. It's going to exceed that, so it's going to surpass this elastic limit, so no good. Calculate the spring constant then. So if the spring constant equals force over extension, the force is 50. Let's look at what the extension was. The extension was 2.5. Okay, so, oops, didn't want to do that. Let me just undo a little bit. So that's where I got 20 from. Add a line to the graph for a spring with a smaller spring constant. So it's gonna be less force for that extension. So it's going to be a shallower line. Question 4 then. A big numeracy question this. So it's all about picking out data from the table. So we've got 0 to 30, 12 seconds, mass there, emissions, and then fuel economy per litre. So the car travels 160 kilometres. Calculate the mean mass of CO2. So the mean mass of CO2, this is 90 per kilometre. So for 1 kilometre, there's 90. So what's it going to be for 160 kilometres? 160 times 90 is going to give you that. And we're looking, yeah, it's grams, so it's all good. Calculate how many litres of fuel. So here's your litres of fuel. So you can get 32 kilometres out of 1 litre. I've got to travel 160, so I want to see now how many times 32 goes into 160, and I need 5 litres. And you can work that backwards then. You can think, well, I can do 32 for 1, and then 32 plus 32 is going to be 64. That's going to be 2 litres. So what's 5 going to give me? And that's going to be 5 times that 32 then. That'll get me 160 kilometres, and that's what I need. Use data from the table to calculate acceleration, which is change in velocity over, should be the change in time there. So I've got 30 from here because it accelerates from 0 to 30. 30 minus 0 is just 30. And then that's why there's the change in v. So the change in v is v minus u. The final velocity minus the initial velocity. And it took 12 seconds. Let me just prove that. So 12 seconds there. And that's how I would do that calculation. 30 over 12 gives me 2.5. I think there's one more calculation with this then. F equals ma to calculate the force required. So I've got my mass and then my acceleration. Where did I get my mass from? Let me just scroll back up to here. It tells me there. So everything in the question, it's all about reading the question. State one other way a car's made more efficient. You can streamline it and you can make them lighter, so you can use lighter materials. Here's your specified prac then for terminal velocity. It's using cake cases and dropping them from a particular distance and then timing it, and then you'd increase the number of cake cases, I think. That's where we're going with this. So state what is meant by the terminal speed. It's the maximum speed that an object can travel when forces are balanced, for 1 mark. Maybe they should have given 2 marks there. But 6 good bullet points now for 6 marks. Describe how you carry out an investigation to find out how the mass of a falling paper cakes affects their terminal speed. So this is something we would have done in class. You set up the apparatus as shown, with the pointer 150 centimeters above the floor. Now it needs to be above the pointer because you want it to reach a certain speed before it hits the floor. You want it to get terminal speed before it hits the floor. Use a balance to find the mass. That's the other thing you do. Drop a single case 20 meters above the pointer to ensure the terminal speed is reached. That's what I was just talking about then. Use a stopwatch to record time. By the way, there's a video on this. Repeat steps and calculate mean. Repeat will with different numbers of cupcake cases. So that's a really basic bullet point there, but that's going to get you marks even by bullet pointing. Again, I'd advise to watch the video on that. Then it follows on with some results. And you need to calculate the terminal speed. Well, you get speed from distance over time. What's my distance? What's my time? I can get my speed. Then we're going to plot that data, which is going to look something like this. So my line's not quite where it should be, and that's why you've got to do it in pencil, because if I did that in an exam and it was in pen, then I don't get another shot at that graph, and it's worth 3 marks. One student suggests that doubling the number of cupcake cases reduces the time by half. Should we see if that's true for 3 marks? Well, I'll get my first case, and it takes 0.9 seconds. So I'm going to double that. So I'm going to increase it. Is it going to reduce the time by half? No, it doesn't. And let's just check again for 4 cases. Does this half? No, it doesn't. Okay, so I guess I've got 2 marks there. Oops. For my other mark, I should have said this does not support the suggestion, but I didn't put it in. Question 6 then, we've got a radioactivity question, and we've got some aluminium going through, and we've got some radioactive source. So it's given us a bunch of isotopes there with their half-lives and the type of decay that they are. So then I'll go to my next page then, and we've got some answers, tick boxes to do, and it's worth 3 marks. Alpha consists of helium nuclei. Yes, that's correct. Alpha radiation is more ionizing than gamma. Yeah, because it's got a positive 2 charge. Strontium-90 has 90 nucleons. Now, a nucleon is just like another word for mass number, so that's correct. So 90 nucleons, number of protons plus your number of neutrons. Gamma radiation consists of low energy. No, it's high energy waves. Gamma radiation only travels a short range. No, it travels a long range. Beta radiation consists of fast moving electrons. That should be, so that's incorrect. So these 3 are incorrect because that should be fast moving electrons. So I didn't need any information from the table there. That was just all previous learning. One of the students suggests that strontium-90 is the most suitable for monitoring the thickness. Explain whether or not you agree. So I've said beta is the most suitable as it would be partially absorbed and blocked by aluminium. And we've got that increase in thickness there. So strontium-90 is beta. It's got a half-life of 29 years. This one would have, so even though this is beta, I could have said, oh, this would have been the better one, but it's got a half-life of 14 days. And in industry, that's no good because you're going to be replacing it every 14 days then. So that's got a nice long half-life as well. Maybe I should have pointed out. Alpha would have been no good because it would have been blocked by the aluminium. You could have gone for gamma, and many people have before, and it's got a long half-life. The trouble with gamma is that it's not that sensitive to, it just goes straight through aluminium, whereas the beta, at least it gets partially absorbed by the aluminium because we're dealing with really thin aluminium, so it can be monitored better. Even though we say that beta is blocked by aluminium, but on a certain thickness, if it's very thin, it's gonna let some through. Explain what is meant by the statement the half-life of strontium-90 is 29 years. Well, it's going to take 29 years for the mass or the activity or the parent nuclei of strontium to half, or decay by half. I should have put decay in there. Then we've got the table that we've learnt. So it's going from 1 over 1 to 1 over 8. Because we always start, if we've got a fraction, we always start at 1 over 1. Your number of half-life start at 0, your time starts at 0. You're probably wondering where I got the half-life of 29 from. I go back to the table, and strontium-90 there is 29 years. So the half-life is 29 years. So for each half-life now is going to be 29 years. Add 29 is 58, add 29 is 87. And then you half this until you get to an eighth. So it's 87 years. This last page then is a bit of numeracy again. So I've got 5 minutes. You need to be aware now if it counts per second, and it's got that in bold, I need to convert 5 minutes to 300 in order to see how many 300s go into 150. So that's what that question is. So recording 150 counts per minute. So what's this per second? It's going to be 0.5 counts per second. How can you improve the accuracy of the results? You can measure for a longer period, and you can take repeat readings. So I hope you got something from this paper.